approach this differently and then come back to it. All right, so we have time dilation. We'll sort of ignore all the length stuff right now. And so the question is this actually accurate? Einstein came up with this in 1905. The theory of general relativity gets its first proof or evidence of veracity in 1918 or so, but it takes another 15 years or so before there's any evidence that special relativity, this time dilation, even exists. So let's run through the muon experiment. So a muon represented by a mu with some sort of charge symbol. So typically, if you're generically talking about a muon, you'd write mu plus, and if it's mu minus, then you just adjust everything else accordingly. This is a muon. It has a mass of about, I want to say 207, yeah, about 207 times the mass of an electron. To give you some idea, it's a subatomic particle, so the mass of a muon is approximately 207 times the mass of an electron. Now these are particles that will decay, so they are coming at us from outer space, and so we get these muons coming in, and they will only live for a certain amount of time on their own before they will break up. And so if we set up a detector here and count the number of muons that come through, then we have some idea of, well, obviously the number of muons that come through. We then set up another detector at a different location and see how many muons we count down there. I did not write down the half-life. That will be important information. Unfortunately, we can resolve that. So the way that these detectors are set up is you take a liquid that is called superheated. Just the slightest vibration will cause it to suddenly boil. You might have experienced this if you put water into a microwave long enough, and when you open up the microwave, the water doesn't look like it's boiling, but as you move it, you jostle it slightly, and suddenly the thing erupts. Any of you experienced this? Yeah, that you basically have created a superheated liquid, so this tiniest disturbance will cause it to boil. So what happens is this is set up just right with the superheated liquid, and as it comes through, it actually, instead of all erupting into boiling, because it's just a very tiny particle, you end up with these trails of bubbles so that you can see the path that they've taken. And then you expose it to a magnetic field, and it will move one way or the other, and you can start to identify the particles, very similar to the master set problem, where I gave you the radius of curvature and I think how fast it was coming in. And you were able to identify the particle. So they go up to, I believe it's Mount Washington, and they set up a detector there, and they set up a detector down here. 1,900 meters difference in elevation. If you work under the premise that you have the same number of particles that are going to, basically you get the same number of particles hitting pretty much anywhere, so that if I get, then it was 568, they counted 568 muons here, you're going to get 568 muons basically at that elevation, pretty much no matter what. That's a valid assumption. And then they counted the ones down here to see what happens. So let's make our predictions as if general relativity is right and if general relativity is wrong. And I do need to look up the half-life. Half-life muon. 1.56 microseconds. So this is the half-life, 1.56 microseconds. Micro, 10 to the negative sixth. So these muons are going to be traveling 1,900 meters. And they were traveling at beta is 0.994.
The board is gonna shut down.
Pardon?
The board.
Oh. Okay, thank you. So they're traveling at 0.994 times the speed of light, and they're going to be traveling 1,900 meters. And the question is, first off, how much time does it take to get down to here? And then how many should be left? Well, I know speed is distance over time, and so time would be distance divided by speed. And so our distance is 1,900 meters. The speed is 0.994 times the speed of light, which is roughly 3 times 10 to the 8th meters per second. So how much time does it take?
About 5.73 times 10 to the 11.
What,
Times
5.73?
Times 10 to 11.
Oh, no, I think you, did you put this in parentheses when you divided?
Oh.
I got 6.37 times 10 to the negative 6
Units?
seconds.
All right. So how many half-lives do we go through in that time? Well, I know one half-life is this, and a half-life is if I've got a group of particles that will sort of randomly decay. Half of them will decay within that amount of time, so then I'll have half left, and then after that amount of time, half of those will be gone. After that amount of time, half of those will be gone, and so forth. So the number of half-lives is important to know how many should exist. And so how many half-lives is this? Oh, that divided by that. Point something?
4.08.
So we have 4.08 half-lives. Now we can very crudely just go, we started out with 568 of them. After one half-life, I'd have half this, which doing the fancy math, 284. After a second half-life, it's not a minus sign, that's an indication. After a second half-life, we'd have 142. After a third half-life, we'd have 71. And after a fourth half-life, we'd have 35 or 36. These are statistics, don't expect exact numbers. So if general relativity is bunk, or sorry, special relativity is bunk, we'd expect to be able to set a detector 1,900 meters below this, since this stuff's coming from outer space, and we would expect there to be around 35 or 36 muons. And as you would assume, that's not what we got. If special relativity were in play here, how much time passes for the muon? From the muon's point of view, the muon is just sitting there, fat, dumb, and happy, and the ground's coming up towards it. So the time for the muon is the proper time there, from the muon's point of view. So I know that t is equal to gamma TB. If beta is 0.994, what is gamma? All right, anyone else get the same thing? Okay. All right, so we have a gamma of 9.142. So from Earth's point of view, we have this 6.37 second times 10 to the negative 6 seconds. That's going to be equal to gamma times what the muons are seeing. So the time that passes from the muon's point of view would be 6.37 times 10 to the negative 6 divided by 9.142, which is
6.97 times 10 to the negative 7.
So what is this prediction? All right, so let's actually, instead of doing the crude, how many half-lives is this? Because, well, actually, how many half-lives is this? If we divide that by the 1.56 times 10 to the negative 6,
.447.
so we have over 4 half-lives that pass if special relativity does not apply, and if it does apply, we have 0.447 half-lives. When you want to figure out the actual number, the general formula here is that, we'll just let A be the amount. A is equal to whatever the initial amount is times 1/2 raised to the time divided by the half-life. So in our particular case here, this prediction here is, we started out with 568 times 1/2 raised to the 0.447.
So we got 416.7.
116.7. So if special relativity has any merit, we would expect to see somewhere around 416 or 417, and they saw 412. So experimentally, 412 were detected down here. This was the first bit of evidence, 1940 or so, in which there does seem to be some credence. '05, big year for Einstein. Came out with this special relativity and the idea of time dilation. 1905, he came out with the basic tenet of general relativity. Took him another 10 years to come up with the math behind it, or to figure out what math to use with it. He showed that, basically showed statistical evidence for the atomic theory of gases, the fact that the lot of atoms in the air, and a fourth one I can never remember. And probably deserved several Nobel Prizes, but in 1920 or 21, they just gave him one Nobel Prize for contributions. You know, at some point, you can no longer deny him. And what was the main reason Einstein did not get a Nobel Prize sooner? Or why he was given only one?
Because he was German, or he worked
Not
with
German. He was German, but it was not his German identity which caused him issues. He was Jewish. Nazi Germany did not pop out of nothingness. The anti-Semitism was running deep. All right. So we have this idea that special relativity is valid. Now let's look at it from the distance point of view. So from Earth's point of view, it's traveling 1,900 meters in, unfortunately I erased it, it was 6 point something times 10 to the, how many microseconds?
10 to the negative 6.
6 point what?
37.
All right, so 6.37 times 10 to the negative 6 microseconds. And from that, we got a speed, wrong symbol. The speed was 0.994 times the speed of light. From the muon's point of view, what's moving from the muon's point of view? So this is Earth. This is muon point of view. What's moving from the muon's point of view?
The Earth.
Yeah. And, well, let's figure out how far the muon says that Earth's traveling. So I know the muon says the Earth's traveling at this speed. And so the distance that the Earth travels is, well, v times t, which is 0.994 times the speed of light, times the time that passed for the muons, which was 6.97, times 10 to the negative 7th seconds. So how far did the Earth travel?
Yes.
6.93 times 10 to the negative 7th? Oh, you forgot to multiply times the speed of light. 3 times 10 to the 8th. Ish. $1,899.5. 1,899.5? No, something's wrong.
I got 207.8.
Yeah,
Yeah, I got that too.
that is more realistic. Did you do 10 to the negative 6th or 10 to the negative 8th?
I did to the 8 for speed of light and to the 6 for the.
That's negative 7 there. All right, so there's clearly a difference in the length from the muon's point of view and from the Earth's point of view. As a matter of fact, the ratio of Earth to this is the Earth's point of view over the muon's point of view. And that should be 9 point something, 9.0, I forget what it was at this point. The gamma.
Nine.
9.142.
9.142, all right. Which is just gamma. So we have the two different lengths. The ratio of the two different lengths is gamma, just like for the two different times. However, which of these is the proper length? Going back to sort of a question I asked before, and then botched it twice. Actually, I botched it once, one of them was correct. But which of these is the proper length? Again, you want to do it from the at-rest point of view.
The 1900.
Yes. Because that 1900 meters, that's the difference between the bottom detector and the top detector. That doesn't change from the Earth's point of view. It does, the distance from that this travels, I mean, the distance between here and here, well, actually, how far this travels does change, or how far away it is, that's better wording, how far away it is does change as the muon approaches it. So this is the proper length here, and so we can generalize it as in the proper length divided by the length is equal to gamma. Or LP is equal to gamma L. Even though I have proper time over here and I have proper length on the left-hand side, if we're